Welcome back. Previously, we discussed about dimensions of some physical quantities, and then we focused more on time, force, acceleration, and all that. Today, we will discuss about the derivation of exact form of a relation between measured physical quantities using dimension. Don't forget to subscribe as you're watching this video. Suppose the period of oscillation of a simple pendulum, let's take for example, depends on the mass m of the pendulum bulb, the length of the thread, and the acceleration due to gravity, that's g. Use the method of dimension to find the correct relation. We have this as example. Solution. We have that the period t equal, let's assume there is a constant k m l and g. Now for dimension, we need to know what these quantities are, so let's start with k we don't know, let's call it x, what power it contains, and then l, let's call it y, then I have g, let's call it z. Now in dimension, we don't consider the constant, so we'll be neglecting this constant. And then I have the period. From our previous lesson, we know that m for dimension for mass is m, capital Mx, and then for length is capital Ly, is power y, and then for g, acceleration due to gravity, we say that acceleration is L minus t minus 2, Lt minus 2, so this will be raised power z. Now when you open this bracket, you're going to have t equal m x l y. This z here, you have what? L raised power z and t minus 2 z. Now let's collect like terms. These two have the same base, so from indices we add the powers. And then we also know that for dimension of period, we have for period that m as 0, there is no mass in period, there is no length in period, and then t is 1. This will give me m x, these two power, you add the base and you add the powers, z and t minus 2 z. Now we're going to equate each of these to its corresponding left hand side. So m, we're going to, from here we can show that, let's equate the letters with the letters or the alphabet. So this will be equated to this one. So you have m 0 equal m raised power x. From our indices, you can see that you can, when the bases are the same, you equate the powers. So the x will be equal to 0. Now second one we talk about is the L. Let's equate L. I have L raised power 0 will give me L raised power y plus z. So I have that y will be equal to minus z. And also, if I equate t, I'll have t raised to power 1 will be equal to t raised to power minus 2z. And then I have 1 will be equal to minus 2z, such that z equal to minus 1 over 2. So we have found the values of y, x, and z. So let's return back to equation 1. Okay, let's return back to the original equation. That's this equation. We didn't name it. This equation, no. Returning back to this original equation and see what we're going to do. This equation. So we've gotten the power of x to be 0, power of y to be 1 half, and this to be minus half. So let's write it. Therefore, x equal to 0, y equal to 1 over 2, and z equal to minus 1 over 2. So let's go back to the equation that we are given t equal to k m raised to power x, and then I have l raised to power y, and then g raised to power z. So here we agreed that we found out that x is 0, so here is half. Let's substitute it back by substitution. I have t equal to k, this will give me 0, so I have l is power 1 over 2, and z is power minus 1 over 2. And then I'm going to have, from indices, I'll have k into l is power 1 over 2 all over g is power 1 over 2. So this will give me the period of oscillation. It depends on the constant, which is dependent on the length and the square root of L over G. If you found it interesting, don't forget to subscribe and click your notification button to follow for other interesting topics to be dealing. Thank you.